Hi students. So today I thought to give you a demo on class 10 mathematics chapter, which is circles. This is one of the widely used chapters and mostly talked about chapters for especially for class 10th, and some questions are asked from this chapter. So I wanted to give you a demo on this particular chapter. So welcome first of all to EdFalco Academy, an epitome of FAAR-o education, which means faster, affordable, reliable, and result-oriented education. So let's start with this demo class, and obviously you can get in touch with us at any point in time uh, to understand anything that is not clear, or if you have any queries, you can definitely reach back to us at any point in time. So let's start with the chapter circles, and I will just briefly describe in another, let's say, 20 to 25 minutes about certain topics, and that will help you understand. And we'll also do a question at the end of the session. So let's start the chapter. So, so we are starting with the chapter called circles. So first of all, to understand the circle, we should understand what the circle means. What is the definition of a circle? So as you already might be aware of, some of you might be aware of, a circle is nothing but a locus of all the points. Locus of all the points that are at same distance from a given point. From a given point. Locus of all the points from a given point. So what does this mean? So two important things here. First is this given point is important, right? Then same distance, and then it is locus, obviously the locus of all the points. So if you understand this, it's in simple terms. Suppose there is a point, right? Suppose this is a point. Let's call it P, and this from this point in there is another point which is sitting at, let's say, a distance of something, maybe let's call it 5 centimeter or whatever, could be any distance. The another point should also be sitting from there at a distance of 5 centimeter. So all such points that are sitting at a distance of 5 centimeter from this point that we have selected, the given point, which is point P, and are all these points, as you can see the dots that I have made. Any point I found, it will be at a distance of 5 centimeter, right? Any point that I take, it will be at a distance of 5 centimeter from that center point. So if I now join all these points, then that path or the locus, another word for path, locus is basically the path or the trace of all these points. If I do, it will become a circle. So that is the definition of a circle. A circle is the locus or path or trace of all the points that are at same distance from a given point P. So having understood what a circle is, and there are a couple of things that we should understand here. One is this point P, which is the given point that we had taken. In general, we will call it center of the circle. Center of circle. Then this distance, which is constant, of course, it is constant distance for any point that lies on the circle. This constant distance, for example, in this case, I had picked up 5 centimeter. That is nothing but my radius of the circle. So a circle can be defined if I know the center of the circle and if I know the radius of the circle. With these two things known, I can always define a circle. So having understood on what exactly is meant by circle, let's move ahead further and try to see what's next in the uh, store for us. So we will discuss about important thing over here, which is nothing but the tangent to a circle. So some of you might be already aware what the tangent means. Tangent is nothing but a simple line that we talk about. So in a circle, what is a tangent, right? It's a tangent to the circle. So in a circle, what is the meaning of the tangent? So tangent to the circle. So tangent is a line to the circle. So let's say I have a circle and I have a line, right? So this is a line and this is a circle. So obviously this line will be called a tangent. Will this line itself is not a tangent, of course, but a line will be called a tangent. So now there are three possibilities if you look at it. This line can be either completely out of the circle, or it might be a line like this, which is actually cutting the circle itself. But none of these two are actually the tangents. So in this case, what is happening? The line is cutting actually the circle. So it is obviously going to cut at 2 points, right? This point A and point B, which we know is nothing is better called as the chord. AB is called the chord of the circle. AB is the chord of the circle. And obviously this line is then cannot be called as a tangent. Okay, it is better known also as the secant, not tangent. It is known as the secant. So AB line is actually cutting the circle. It is not the tangent. Is this line a tangent? No, this is also not a tangent because it is simply like going out of the circle. There is a third possibility also, which in which line is just touching the circle. So let's say it is this point is on a circle and the line simply touches it like this. So only one point on the line, one point of the line, right? On the line there is one point, and on this circle there is one point, and they are actually in contact, right? If you zoom this, it is basically that, yes, it will be basically that you are talking about a circle, and there will be a circle portion, and there will be a line which is touching it, right, at one point, at this point. So a circle is there and a line is touching it at just one point. If you zoom it and see. So that line is basically known as the tangent to the circle, right? So we see that there could be three possibilities. One is the line which is already lying outside, the line which is actually cutting the circle, and the third is actually the line which is just touching the circle. And this line is nothing but the tangent to the circle. We call it tangent to the circle. Now, can the tangent be drawn from inside the circle? Can the line be drawn from outside the circle? That is what we will discuss next. So let's say you have a circle. Now, if you want to make a line which passes through inside of the circle. So suppose there is a point I have just picked a point arbitrarily, which is inside the circle. So now if any line, if I want to pass it through it, any line, it could be this line, it could be this line, it could be that line, any line, you understand, right? So all these lines, none of them are actually your tangents. They are becoming your seconds, right? So none of these lines are actually the tangents because so the what is the point that is coming out? That line drawn from inside of the circle, from inside of the circle cannot make tangent, cannot make a tangent line. It is clear from this picture. If you are trying to take a point inside and try to pass that any line from inside of the circle, obviously those lines are not going to be tangent because according to the definition of the tangent, it should be touching the circle at one point. Here, what do we see? It will start cutting the circle at 2 points, which is not a tangent. If the another situation is if obviously if there is a point which is on the circle, which is on the circle. This is the circle, and this is on the circle. Pardon my drawing, it's not very good, but yeah, so you can imagine that it's a circle, and then there is a point which is lying on the circle. Can the tangent be passed through it? Yes. In this case, one and only one tangent can pass, and that line will be this line, which actually touches the circle. A line like this, which is actually touching the circle, will be your tangent. Obviously, multiple lines can pass, like this also it can pass, but this will not be a tangent. But what point is being said is that if there is a point on the circle, at least one line will be there definitely, which can actually, which can be made, which can be called as the tangent of the circle. There will be one line which will be called as the tangent of the circle. Uh, but that doesn't mean that you cannot have other lines. Obviously, a line like this is also possible, but this is not tangent. It is cutting here as well as it is cutting here. So that means it is going to cut the circle at 2 points. But what we are trying to say is that there is one line, which is this line, which can pass through this point, and it will be just touching the circle at 1 point. And this line will be the tangent. So in this kind of scenario, when the point is lying on the circle, P on the circle, right? This there is a possibility to make the tangent. Tangent possibility is there, right? Now let's move on to the next possibility. The next possibility is if the line, if the point is outside the circle. The point is outside the circle. So let's say there is a circle and there is a point which is outside the circle. So we talked about inside the circle, no possibility of tangent. On the circle, if the point exists, then there is a possibility of one line which can be made as a tangent. And if it is outside, again there are multiple lines that we can draw, but there are possibilities to draw two tangents. What are those two tangents? One line can be drawn like this, which actually touches the circle at one point. Right at this point it touches. And same way you can draw another tangent as well, which touches over here. So two tangents are possible from a given point P, which lies outside of the circle. Two tangents possible. And later we will learn that these two tangents will have the same length and all that, whatever the theorem associated with that. But at this point, what we are trying to find out is that two tangents are possible. Two tangents are possible if we are taking the point which is outside the circle, right? So these are certain basic things that were required first to understand. Like in the case inside the circle, we cannot have the tangent. In the case if it is on the circle, then one tangent is possible. If the point is lying outside the circle, then two tangents are possible, as you can see over here. Okay, so with that, having said that, let's move on to one of the theorems. So the theorem says basically that tangent, so this is I'm talking about a theorem. Theorem means that it is always valid, right? Theorem is something which means it is always valid. So tangent to a circle is perpendicular to its radius. So tangent to a circle is always perpendicular to its radius. So what does that mean? Let me make a better circle. So here is the circle. So a tangent line, let us make a tangent line. Any line is fine. So that's a line which is basically the tangent. It is touching the circle at one given point, which is this point P. And let's say that the center of this circle is O. And let's join O and P. Obviously, OP will be what? You can very well understand OP is nothing but the radius of this circle R, denoted by R. So R is nothing but the radius of this circle OP. Okay. So what the theorem is telling is that the tangent, which is this line, which is tangent, is perpendicular to the radius. So this angle over here is 90 degree. That's what it is trying to say. So how do we prove this? That indeed this is the case. So in order to prove this, let's make another line, assuming that we have some other point over here, and we make a line like this. So assuming this, we have made another point. Let's call this point as Q. So we are making another point which is slightly away from point P. Okay. So which is slightly away from point P. Let's call it Q point. Now obviously, according to the definition of the tangent, P is the only point which is touching the circle, right? So the moment we move away from P, right? Obviously, it is going to be not on the circle. First of all, the point Q is not going to be on the circle. It's going to be on this line. And you can see also from this diagram very well that OQ, the distance O to Q, which is this distance, will obviously be greater than O to P. So any other point if I take on this line, so Q was just for one sample, but any point if I take, let's say this point or this point or this point, whatever, if I try to join up from with respect to O, or I try to join that point from O, right? Like this, like this, like this. All of these length, right? OQ. Suppose here it is OM, or here it is ON, for example, ON, or here it's let's say OA, whatever. All this OA, ON, OQ, OM, all those will definitely be greater in length than OP because that is the shortest distance that I have. Right, all other lines, obviously, as you can see from this picture, that all of them will have higher distance. Now, what does this signify? This signifies that the distance OP is the minimum distance, right? Is the minimum distance is the minimum distance. That means P is at the least distance, is at the least distance from O. Right? So if I talk about this line, let's say call it line L, the line itself is called as L, let's say, this entire line, distance from a point, right? So distance of this line from a point. So you know that any distance, that whenever there is a talk about the distance, so let's understand this. So if suppose you have a line and there is given a point, so what is the distance between these two? If the question is asked, what is the distance between these two? Is it this distance? Is it this distance? Or is it any other distance? So the distance is basically the shortest path, shortest length, shortest length. So the shortest length will definitely come if you make this directly perpendicular from this line. So this will be D. If the length is D, that is the shortest distance between this point P to this line L. And that will come only if you have this as 90 degree as the perpendicular line from here to here. It's you can understand it's like a it like it's a common logic, right? That if from here if you are drawing, if you want to reach, let's say from anywhere on this line, suppose you are on this line is like a road, and you are anywhere present on this line, right? So if you have to take the shortest path to P, right? The shortest distance from here to here. The shortest will be when you directly start moving towards P. You are on this line at this point, let's say at here, and you want to go to P. So what is the best way to go to P? What is the shortest distance? Directly heading towards P, right? The directly heading towards point P is what? You are going perpendicular to this line, exactly perpendicular to this line towards point P. So now returning back to our original discussion, we are seeing here also that your only point P is at the least distance, is at the least, has the least length from O. That means this OP, which is nothing but the radius, must be perpendicular to the tangent. And that is what this theorem was telling. That tangent of a circle is always perpendicular to its radius, right? And that's how we have proved it, that since P is at the least distance from O, therefore OP must be perpendicular to, this is way of writing perpendicular to line L, which is nothing but the tangent line. And this is valid for now any circle, right? If you take any circle, whatever radius, and there is a tangent, it will be perpendicular to the radius of that particular circle, right? So, for example, if I would have made the tangent over here, suppose I would have made the tangent over here. If you would have drawn a radius like this, that would also have been perpendicular to this. So that would have been the shortest distance or the shortest length between the line to the circle center. So I hope this is clear. So let's move on to the next theorem. Okay, so now we have also understood about the tangents. We have understood the possibilities of making the tangents, right? If there is just one point on the circle, only one if you are taking the point on the circle, then there is a possibility of just making one tangent. And then we have also studied that if you have a point outside, from the point outside of the circle, you can make actually two tangents. From a point inside the circle, you cannot make any tangent. Also, we looked at the theorem that the tangent is always perpendicular to the radial line or the radius of the circle. Now, in the same line, we will talk about another theorem. So remember that we were discussing in the beginning that if suppose this is my circle, and let's say I have tangents drawn from 2 points, from point outside the circle. Sorry, from point outside the circle. So let's say I'm just trying to make that picture first. So from this point, I have drawn 2 tangents, right? This is how it should look like, right? Yeah. So this is tangent 1, let's call it T1, this is tangent 2, T2, and the point from where it is being drawn is, let's call it point P, and this is my center of the circle. C is the center of the circle. So now the theorem is telling is, theorem says that length of tangents drawn from a point outside the circle, is same. What is same? The length of the tangent is same. So what, in simple language, what it is trying to tell is that if you have this point P, you have drawn one tangent from outside, the point P is lying outside of the circle. You have drawn 2 tangents, PT1 and PT2, these are the 2 tangents. So the length, let's say this is and this one is, let's say, touching the circle at point, another point, let's say OM, let's call it OM. Let's call it O and M. So O and M are the points at which these two tangents are touching the circles respectively. So you have line PM and line OP. So the length of the line OP, this length from here to here, that is my length, and this length is from M to P. This is also my length L. These two lengths are going to be similar. They have the same length. That is what this theorem is talking about. So what is the proof of this, right? So in order to prove this, let's draw, first of all, let's try to draw another line. What type of line? Let's join the center point to this point P. Okay. So I got one more line, which is this line PC. Okay, this line PC I have drawn. Also, let's join these two lines. This line over here and this line over here. Now you will understand why I'm drawing all these lines. Um, so I have made all these lines. So these lines are all my constructions I have drawn, right? CO and CM and PC. These are the three lines I've drawn. Now you can see, if you look at it carefully, there are two triangles that are getting made. One is triangle, one triangle is triangle POC. I mean this triangle POC, the upper triangle. And the another triangle that is getting made is triangle PMC, right? The lower triangle PMC. Let's analyze these two triangles in more detail. If you look at these two triangles, the first thing is angle COP, which is this angle, which is this angle over here, COP, is same as angle CMP. CMP means CMP, this angle. And because both of them are equal to 90 degree, why they are equal to 90 degree? Because just we talked about that any tangent in the previous theorem, we just talked about that the tangent of a circle is always perpendicular to its radius, and that is why this angle must be 90 degree, and the same must be true for both these tangents, right? So for this triangle as well and the other triangle as well, this angle COP and angle CMP must be 90 degree. So that means these two are clear. Then another important thing is your angle, not the angle, sorry, the side CO and the side CM are equal. Why? So when you are writing your answers also, you should write it like this. Here I'm putting Y, but you have to put the definition. Like instead of Y, in place of Y, you will be actually putting that the tangents of a circle is perpendicular to its radius. So that is why you are saying that okay, these two angles are same and they are equal to indeed 90 degrees. So same way CO is equal to CM, I'm saying. Why? The reason is that CO and CM are nothing but the radius of the circle. So this is also R and this also must be R, right? Both of them must be the same value. So that is why they are equal in their side length. Now coming to the third one, which is CP. CP. CP is common in both. CP is common in both. CP is getting common in both, right? So that means what? This side is also same for these two triangles. Now you can see here, this is nothing but right angle triangle. This is R. Okay. CP is common in both. CP, if you look at it, If this angle becomes 90 degree, the angle COP or CMP becomes 90 degree, then it becomes a right angle triangle, right? Both of these triangles are right angle triangle. And in the right angle triangle, you can see that CP is basically the hypotenuse, and CP is common. So you can say that CP is also equal in both the triangles, right? So H is the another parameter, H, which is hypotenuse. And the third, CO and CM are same. It is defining the two sides of the triangle. So it is S. So by the theorem RSH, right? By the congruency RSH, you can now say, based on RSH congruency, you can say this topic of congruency is already dealt in ninth standard in detail. So um, if any confusion is there in that, then we can certainly discuss. But for now, I understand that it is already known when we are in class 10. So RHS is the congruency top is the baseline of establishing the congruency between these two triangles, and that means what? Your triangle that means that your triangle POC is congruent to triangle PMC based on the RHS congruency. Right? Now, if this is the case, then obviously the corresponding sides, corresponding sides of the two triangle also must be same. So in this case, PM is corresponding to PO. So that is why PO, that is why you can now say that PO will be same as PM based on the fact of CPCT, the corresponding parts of the congruent triangle. So this is what establishes our theorem that PO is equal to PM. And that's what the theorem was talking about in the beginning. That theorem was saying that the length of the tangents, this tangent and this tangent, length are equal. That means PO is same as PM. And we have what we have done, we divided it into two triangles. We found that these two triangles are congruent based on the fact that this angle over here, COP and CMP, are 90 degrees. They have the common sides, which is R and R, radius of the circle. And this third one, which is the hypotenuse, is nothing but coming out to be the same or a common side of both the triangles. And therefore, I can say these two triangles are congruent. And based on that, corresponding parts of the corresponding parts of the congruent triangle are are equal. I can say that PM is equal to PU. And that is how I establish the theorem that indeed the lengths of the two tangents are equal. And now this is true for any of the triangles, any circle and tangent scenario where you are making a tangent from a point outside the circle. The tangent lengths are going to be same. So hope this is clear. Okay. So now let's look at this problem, which is partially based on whatever we discussed so far, and obviously we will have to carry some more things into it. So let's see this problem. Let sigma 1 be a circle with the center O. So you you can see this is the bigger circle, which is called as sigma 1, and its center is at O. And let AB be the diameter of sigma 1. So AB line is the diameter of this sigma 1. AB is the complete diameter. Let P be the point on the segment OB different from O. So on the segment OB there is a point P. Any point, anywhere that point is met between O and B, and that is point which is that P is different from O. That's what it is saying. Now suppose another circle sigma 2 with the center P lies in the interior of sigma 1. So with this P, there is made a circle, which is the inner circle, you can say. And this circle is completely lying within the outer circle. That's what it is telling. So the inner circle is being called as sigma 2, the outer circle is sigma 1. Now, tangents are drawn from A and B to the circle sigma 2, intersecting sigma 1 at A1 and B1. So respectively. So what is being told is that there is a tangent drawn from point A and B on this inner circle. So this tangent A1 is intersecting is basically touching the inner circle at point C and is intersecting the outer circle at A1. Same way from B there is made a tangent on this inner circle which is touching the inner circle at B, and then it is going and intersecting the outer circle at B1. So you can see A1A is basically the tangent and B1B is also a tangent to the inner circle. Then what it says that mm, respectively such that A1 and B1 are on the opposite sides of A and B. So that we can see that A1 and B1 are on the opposite sides of A and B. Now A1B is given as 5. So A1B is 5. So this is your A1B, this is given as 5. And then AB1 is given as 15. AB1 is given as 15. This is given as 15, right? And OP is given as 10. OP is this from here till here. From here till here it is given as 10. So find the radius of sigma 1. So we have to find the radius of the bigger circle. That means AO we have to find. Basically we have to find AO. So pause the video and try this problem at your end, and then let's see if you are able to solve it, and we'll see the solution of this. So now let's have a look at the solution. So before that, let's do some constructions. So let's join these two points and also join this one. So we have joined C to P and we have joined P to D. So obviously you can see that this is nothing but the radius of the smaller circle. And based on the theorem that we just learned, that the tangent must be perpendicular to the radial line. So therefore, this angle must be 90 degrees. That's what we just saw in our theorem. Same way, this will be perpendicular to this angles must be 90 degrees because this one is the radial line, PD is the radial line, and BD is defining the tangent. So they must be 90 degrees to each other. So we have found out at least this much so far. Now another thing that we can also, if you remember from your ninth standard, that if suppose there is a circle and you are making a triangle inside the circle such that one of the sides of the triangle is the diameter of the circle, then the third point, wherever it touches the circle, on the third point, if third point is on the circle, then that will be in subtending an angle of 90 degree. So and this was the implication of another theorem which stated basically that if suppose you have a circle, so you have some arc of the circle, let's say this arc we are talking about, and this is subtending an angle of, let's say, theta at the center. And the same arc, if we take it on the other segment of the circle, like for example, this is the center of the circle, and let's say I have taken it on any other point on this segment, the remaining segment of the circle, which is this segment, then that is going to subtend an angle of theta by 2. That is half of whatever is being subtended at the center. And now the moment you make this theta as 180 degrees, right, it will convert automatically into this picture. That means this is your arc, which is a semicircle now, and this thing is extending an angle of 180 degrees at the center. At the center, this entire arc, semicircular arc, is subtending an angle of 180 degree at the center. And therefore, that same circular arc, if you make any point on the other segment of the circle, be it here or be it here or be it here, anywhere, it's going to maintain an angle of 60 degrees. So it's going to make an angle of 90 degrees. Sorry. So it is going to be a right angle triangle in that sense. So that based on this logic, you can directly see that AB is basically my diameter and A1 is a triangle. A1 is the A1, A and B is a triangle with AB as the diameter. So it is but necessary that A1 angle must be 90 degree. This angle must be 90 degree. And the same logic follows on the other triangle also, which is AB1, which is the bottom triangle, that it is its diameter is the side of this triangle. Therefore, this angle also must be 90 degree, right? So at least now we have this much so far. Now, since these two are 90 degree, if you look at it, since this angle is also 90, this angle is also 90, therefore definitely this line will be parallel to this line. Same with if this is 90 degree over here and this is also 90 degree over here, that means this line also must be parallel to this line, right? So these are certain things that we are now aware of, correct? So far we are aware about these things. Now let's see what else is needed. Now, if you have observed this triangle a little bit carefully, this triangle and the similarity of the triangle can be used here. So, although these are ninth standard topics, which I believe like while you are solving for the 10th problem, you will already have this clear. But in case if it is not, no need to worry. If you come to our classes, if you join our classes, or if you are joining our online classes, we will make sure that you are clear with these steps before you actually go on the 10th standard problems. So, but for now, I'm assuming that pretty much everything on the uh, on the similarity of the triangle is clear. But still, I will give a brief background. So you can see that if suppose that there is a triangle, and in that triangle there is another line which is parallel to the base. So this line is parallel to the base, and it intersects it bisect it intersects the circle. Okay. So now, obviously, if suppose ABC was your original triangle and now AMN is your another triangle, then AMN is going to be similar to triangle ABC. And the moment we have that, there we can write multiple ratios of similarity, right? Like AM by AB will become equal to AN by AC, will become equal to MN by BC, and other and things like that we can write, right? So we will follow the same logic in these two triangles as well. So let's see what happens if we follow this logic in the triangles that we have. So if you look at these two triangles, now if you look at the triangle A1B, if you are looking at this triangle, you can see that triangle ACP will be similar to triangle A1B. Why it is similar? Because angle A is same. This angle C is 90 degree. Same way angle A1 is also 90 degree. And angle A is same. Obviously, the third angle is also going to be same. So it will be just based on a similarity. All the three angles are same. Therefore, these two triangles are similar. So now these two triangles are similar, right? Now, once we have established that fact, we can directly say that AP by AB will be equal to, which means AP from here to here by AB, which is the diameter of the circle, will be equal to small r. We have assumed that this smaller inner circle has the radius r by 5, which is because this length is 5. So r by 5. So you can write the similarity like a similarity ratio like this for this particular triangle. Same way, if you look at the another triangle AB1B, AB1B, again triangle APD, which is this triangle APD is similar to triangle A, similar to triangle BAB1, right? Again, there is a similarity that we can see. Now, based on this, again, I can write BP by A, AB, BP by AB will be equal to, so here in this case, this is BP, and this again AB is basically, or BA is again basically the diameter of the circle, will be equal to the ratio of R by 15. R by 15. Now let's imagine this is my equation 1, this is my equation 2. Now if I add these two equations, if I go ahead and add these two equations, I will get AP plus BP by AB will be equal to R by 5 plus R by 15, which is nothing but 4R by 50, right? And AP plus BP, AP plus BP, as you can see from this picture, AP plus BP is nothing but AB itself, right? So that means it will become AB by AB on the left hand side is equal to 4R by 15. And that means AB by AB will give you 1, and therefore R will ultimately turn out to be 15 by 4. So R is the smaller circle's radius, which is coming out to 15.4. If you convert it, it will become almost 3.75 units, right? So that is about R. But is our work done? No. Our work is to find the bigger circle's radius. This is something that came in between, and we have found it out. That smaller R is basically 3.75. But now another important thing that we can find now is is also that we can now tell that what is AP by AB. We know from here, if you look at it, AP by AB was equal to R by 5, right? So therefore, AP by AB can now be written as R by 5. R was what? 15 by 4 by 5. So that means it is 3 by 4. So AP is basically 3 by 4th of AB. This is important. And same way, if you look at this relation over here, BP by AB, BP by AB, that is equal to R by 15. So that means BP by AB is R by 15, which means it is 15 by 4 into 15 at the bottom. 15, 15 cancels, it will be 1 by 4. So BP will be equal to 1 by 4 of AB. So what are we seeing here? We are seeing that if AB is my complete AB length, then this much from A to P, from here to here, it is 3 by 4 of AB, and from here to here, it is basically 1 by 4 of AB, right? So this is what we are seeing. Based on this, now we can have a relation. What relation we can have? The relation that we can have is this. If you look at this line AB and assume that AO is basically AO is nothing but R, right? The radius of the bigger circle that we are trying to find. So A to O is R. Then this much is already given as 10, right? So R plus 10 plus we know this is equal to 1 by 4 of AB. AB total is how much? It will be 2R. AB total is 2R. So this is the entire A to B length. So therefore it must be equal to R, right? So if you count from A to O, it is R. From O to P, it is 10. Plus from P to B, it is 1 by 4 of AB, which is 1 by 4 of 2R. So it will become equal to the entire AB length. So it should become equal to 2R, not R. Sorry. It should become equal to 2R, which means it becomes ultimately the entire AB length. So therefore, the equation that we get is R plus 10 plus 1 by 4 into 2R, which makes it R by 2 is equal to 2R, right? If you further proceed, 3R by 2 plus 10 is equal to 2R. Now it's a matter of simple solving. So if you send 3R by 2 on the other side, it will become 2R minus 3R by 2, which makes it R by 2. And this is equal to 10. That means R will be equal to 20. So that is your answer. R is equal to 20. Now, if you look at it from this figure, r is equal to 20 means from here to here it is 20. From here to here it is 20, right? So that means this and this much is 10. 1 by 4 of 20 is 1 by 4 of 40 means 2r is also 1 by 4 of 40 is 10. So from here to here also it is 10. So 10, 10, and then 20, right? So this side also it is 20 total, this side also is 20. So the radius of this circle is, of the bigger circle is 20. 20. So that was the end of this problem. So here you can see we have couple of things that we used. One is the usage of the theorem that we just talked about, which is about the tangent that gave us 90 degree, right? That gave us 90 degree. Then another theorem we used, which gave us 90 degree here, right? And then we used also the similarity of the triangles, which again gave us some relation between r, which gave us the value of the inner circle, which is r, and then with some manipulations and some further calculations, we got the value of relation between the overall diameter of the circle and this line PB and AP, and then we were able to form a equation of the AB, right? And based on that, we were able to find the bigger circle radius, which was radius of AO, the well length of AO. So hope you enjoyed this problem. I agree that it was not a very easy problem. It required couple of steps and couple of different things to understand before we can actually go into this problem. But the purpose is that if we are able to get a good hold of this kind of problems, then doing the academic problems and doing your school problems will become quite easier. So obviously, when we study, we will go with further smaller problems into each of these steps. But for the demo purpose, I tried to select a problem which has couple of things involved, so that we can actually show the value of the entire problem. So with that, I would like to close this demo class for class 10. You can always reach back to us for any queries, our or any questions that you have. You can always reach back to us for if you want to join our online or offline courses. Um, and if you want to have access to our course material, which will give you a very broad understanding, deep understanding of each and everything. So um, keep studying, keep doing good problems, and see you there. Thanks for watching the video. Thank you.